morning. Welcome to the first Breakfast with Relog of 2021. Relatively auspicious day, the inauguration day for Joe Biden. We're getting rid of Donald Trump, but hopefully lots more exciting local things happening, like our webinar on floors. So this morning we're going to actually talk about industrial floors for warehousing and distribution centers. And maybe some of the things are common and needed for manufacturing and other facilities, but I'm sure there are special needs in those situations that are relatively different. I'm hoping to have a really exciting session this morning. We're going to be talking about different approaches to similar solutions, not to say one's wrong or one's right. They all have a valid answer, and the professionals and the people that we have on as our panelists today and presenters are experts in the field, and they're going to hopefully give us some good insight, and hopefully during the question and answer session and the panel discussion, we'll have a good discussion and banter and resolve some controversial issues, and hopefully there's no fighting and everyone's pleasant to each other. So first of all, the first person who's going to speak is myself, and I'll be acting as the manager of this whole session today. And I'm just going to give you a little bit of a background and introduction to industrial floors, and that should keep us going for the first 12 minutes. So, I mean, it all starts with a customer from a perspective of Relog. When we look at retail and we look at what we do in developing distribution centers. So, for example, you walk into a supermarket, you find the stock on the shelf there, you pick them, you pay for it, and you go home. And no one really thinks about the process, how did it get there, and it's relatively easy. Today, with e-commerce and COVID and the growth of e-commerce, you click on the internet and the next day or next hour, something drops on your doorstep. It's relatively simple, but you haven't thought about the complex process behind the scenes, what's happening to actually get that product to your door. And previously it used to take weeks, and now it takes hours or minutes. And people are talking about drones that will lift off from a distribution center and drop it at you. But at the end of the day, all of those distribution centers have floors, and that's what we're going to talk about. So really, how does that supply chain influence that consumer experience? And the most important thing is when you buy a product from a supplier as a retailer, the cost is the same. But the differentiator is when you take it from the supplier to put it onto your shelf at the store, which is your supply chain. And therefore, you're looking at transport efficiency, DC, operational efficiency. There's the ideas of centralization and decentralization, economies of scale, innovation in the DC design, logistics, and supply chain strategy, how you can optimize process. But all of them result in a greater in-store efficiency and cost savings. And therefore, cost is a key criteria. So if you're doing something in the supply chain that's going to influence your costs, you're going to be adding to the cost to the supply chain and giving yourself a negative impact in your competitive edge. So everything is around fit for purpose operations. We have storage, we have the capacity of the storage, we have the people in there, we have the throughput, we have the costs, we have the resources, and everything's around balance, where we're looking to increase productivity, efficiency, accuracy, and payback, but reduce energy, labor waste, and obviously reduce our costs. And that then leads us to floors. So the best building investment you can make is on the floor. If the floor is wrong, all operations are compromised. It's disruptive to replace. It affects your machine life. It affects your maintenance on machine. It costs you money. It affects your productivity. You end up slowing down your operations. Your sustainability and the life of the facility is affected. And you end up with operator fatigue. So, and that's just due to some of the problems we have with floors. I'm sure there's a lot that I can go through. So from our perspective as industrial engineers designing these distribution facilities, it's important that we try get the floors right. And the floors are relatively small, and everyone looks for the cheapest option, but the floors are one of the smallest components of cost in the overall development and have the biggest lifetime impact. And it's often underestimated. So if I can convince people to actually not look at floors as a cost issue, but look at it as a life cycle cost issue, and look at it in terms of trying to get the best floor and spend the money, it's the best investment you can make in building a building. Often little attention is often given to the operational requirements. People assume it's a bit of concrete and concrete strong and you can just drive on. And often that's what happens in the design of buildings. Obviously, we as industrial engineers have learned this process through this, and we understand what's happening in the floor, and we've learned through mistakes and all the problems, and this has led us to actually become lay experts in floors. In the old days, we had small warehouses, limited traffic, low loads, basic machinery, forklifts with rubber tires, reach trucks up to 7-8 meters. So it wasn't that critical. But today, it's a different life that we work in. And it's becoming more and more critical. And if you get the floor wrong, it's a problem. Machinery's got higher. You can end up with crane facilities of over 50 meters high. You can end up with turret trucks at 18 meters. Reach trucks are going to 14 meters. Forklifts are lifting to 7-8 meters, what was there. And we've got much higher speeds on these machines. We've got more workload. We've got bigger distribution centers. We're building distribution centers of well over 100,000 square meters today that are doing anything up to 5 million cases a week. So it's significant volumes and number of machines on the floor moving. And there's a lot of traffic on these floors, and therefore the effect of the floor on the machinery and the operation becomes quite critical. So it's a whole new learning. The criteria for good floors, obviously levels. We're going to have Daryl, Eddie talking about TR34, and obviously the floor needs to be within a tolerance of level so that the machines don't rock and the machines don't sway and you don't knock the racking. And for different heights of operations, you want the right levels. Obviously the loads, and especially now that we are building higher and higher distribution centers, the concentrated load on the floor is significant, and therefore the floor needs to be designed thick enough or strong enough to be able to take that load. The other thing is durability. The life of a building is 15, 20, 30, 40 years. The floor needs to last that life. Then there's changes that happen during the life of the building due to curling as the floor cures, shrinkage, there's cracking, degradation. We've got to make sure those don't happen and that doesn't affect the floor. There's operational flexibility. You may start off an operation as reach trucks and then move it into narrow aisle or different orientation, and you've got to have that flexibility to change around over the life of the building. Your equipment wears out after 3 to 5 to 7 years. You depreciate it, and you come in and there's new technology, and then at some point in time you can easily change the equipment. You can't change the floor in the building. And finally, as I started, cost is a key criteria, because if you get the floor design wrong, you can actually spend the cost of the installation of the floor in about 10 times over in terms of maintenance on machines and the floor repairs that you have. And we've got typical floor issues, and these are things that we see. These are pictures from some of the sites that we've worked on. A lot of it's around joints, delamination, breakup, dusting, surface delamination, looking at the abrasion, the wear and tear on equipment, joint breakups, spalling, lack of load transfer, panel rock. I can go on, curling of panels. And as a result of that, that level tolerance that we spoke about in the beginning, that we designed to in the TR34, falls away. And then sometimes you end up the worst case, structural failure, and it makes a floor unsuitable to the operation it was designed for. And you end up having to either move the whole operation out, break out the floor, put a new floor in, or throw a new floor on top. And we've done that with certain clients. So we've had that type of situation previously. And how are these issues being addressed? We've looked at joints, the panel size, reducing joints. So in the old days, we used to have a saw cut at 4.5 by 4.5. Today, we've gone up to about a 32-meter panel, which is about 1,000 square meters. And you can see there's no joints in that panel, whereby if you traveled across that previous panel, you would have crossed 8 joints. And that's 8 points of failure, 8 points of maintenance, 8 points of wear and tear in your machines, 8 curling instances. So just by moving to larger points, you're reducing joints, you're reducing that effect on your machinery, on your operation. There's different reinforcing, there's fiber reinforcing steel, there's post-tensioning to reduce shrinkage. There's different construction technologies and methods. There's different sealings, different ways of curing, different construction equipment and accuracy that people are looking for. Trying to get the levels, you're looking at the temperature and environment that you work in, and your land and ground conditions are important, because the floor is only the part of the overall load that's taken. The groundworks underneath, the layer works, all come to make up a good floor. And I'm sure the professionals on this call will talk about some of these things. There's different joints and joint technology. We had the saw cuts. We went into straight joints, which had dowels or plate dowels. We then had the omega joint. And today we have a thing called a cosinus joint, which links in a different way and also doesn't allow machines to go over and make a lot of noise. So it works quite well. There's different concrete. Basic concrete was cement, stone, and water. Today we added admixtures, plasticizers, non-shrinkage, grouts, etc. And we're getting into a third generation where we're looking at hybrids, where shrinkage and low water ratio concretes are combined with fiber to allow larger panels with less joints. And that's what our drive is all the time, is to look at that. So what makes a good floor? It takes the operational loads, the static and dynamic, meets the operational requirements, allows the machinery to travel without any influence from the floor. And it doesn't dust, deteriorate, or even abrade on the wheel, have abrasion on the wheels. And that's important. The more important issue is the actual structural design, the actual load strength, thickness, sub-base, jointing, and it all influences our ability to operate on that floor. A good design and operation efficiency gives you sustainability. Through the design of optimized distribution infrastructure, we create sustainable operations and give a competitive edge to our customers. So it's best practice, the best ROU, your life cycle cost over the entire supply chain is implemented, and your productivity becomes world-class with Optima. So your optimized facility operations all lead to sustainability as your core. And we look for lowest costs, a lean supply chain, and all of this, the floor fits part of that. Optimizing what's happening with people, equipment, your time, your energy, your resources. And you get that wrong, you've actually got a problem in the way your floors are working. So guys, that's the end of my presentation, and the next person that's going to be talking will be Sebastian Doctor. Just a bit of introduction on Sebastian. Sebastian obtained his degree at the RWTH Aachen in Germany. He emigrated to South Africa in 2001. I've worked with Sebastian probably over the last 20 years, significantly, 15 to 20 years. And we've built a lot of distribution centers. He was part and parcel of our introduction of the fiber reinforced large panel designs into South Africa, which have taken off. The first ones being at ShopRite. And he's done a lot of warehouses with me and probably outside what we've worked on. And so he'll look at some of the issues around the floor design and the effect and the experiences with fiber reinforced floors. I'm going to stop sharing and over to Sebastian, if you can switch on your screen and your mic and start sharing. Sebastian, are you there?
Okay, thank you, Gary.
Oh, sorry. Clicked you. Okay, you're back. Unmute.
Okay, thank you. Let me share my screen. Okay. Okay, let me start with saying good morning to everyone and to wish you a happy new year, 2021. And let's hope that will be a better year than the last one, which should be hopefully easy to achieve. Gary, thank you for the introduction and for the invitation to this panel. And yeah, thank you all of you for your interest in this exciting topic of concrete industrial ground floors. So I thought when we think about industrial ground floors, we must begin with the industry that these ground slabs are actually serving. And so I'm picking up here on Gary's earlier presentation. The goods distribution industry is a very dynamic industry, always looking for technological advances to increase efficiencies. And this is where our floors come in as a foundation. These industries are relying on the ground slab for their operation. So as an independent structural consulting engineer, our main role in this context is risk mitigation. The earlier we get involved, the better, in order to identify current needs and future opportunities for the business and how to adapt the design and the specification to suit those best. And
Sebastian, sorry to interrupt you. We're not getting a screen sharing from you.
Okay. It says that it shares here with me. Can you see it now?
We can see it now. Thank you very much.
Okay. You didn't miss much. I'm going to go back one slide then. This is quickly our introduction slide. And when I started with the introduction on the distribution centers and our role as engineers. So the ground slab is not more and not less the very foundation on which this entire distribution business is relying. So we like to spend time with the clients and the logistics engineers, the likes of Gary and Relog, to learn about their needs, and we like to spend time with the clients to educate and manage their expectations. There's many misconceptions about floors. Cracks, for example, are usually not failures, and they can be repaired easily, or often just left as they are if hygiene conditions, for example, do not dictate otherwise. Maintenance, a dramatically overlooked item. Joints need maintenance. So we would like to prepare for this maintenance in the tender documents. And then compliance with standard. This is an important step in risk mitigation to make the risks associated with the floor insurable. This is much more important than any guarantees. So let's talk about quickly what steel fiber reinforced concrete actually is. So you all know that concrete is a brittle material with a good compressive strength requires steel reinforcement to assume any tensile forces after the concrete has cracked. So in traditional concrete, this work is done by steel bar reinforcement. I guess most of the audience would have seen this and know this. So with the steel fiber floor, the steel bars are simply replaced with evenly distributed high tensile steel fibers. So those fibers are added to the concrete on site into the truck just before the concrete is placed. And then they form a composite material, just as any other bar reinforced concrete. So what do the fibers actually do in the concrete? So the purpose of the steel fibers somehow and somewhat seem to be misunderstood. So I thought a little guidance on this would be useful. The main purpose of the steel fibers is to provide we call it residual tensile capacity in a concrete element after it has cracked, just like bar reinforcement, even though much less than bar reinforcement at common fiber dosages. So this is in use for structural design and especially effective for heavy rack supporting slabs. So under point loads, we can exploit this residual tensile capacity to get a better moment capacity out of the equations and effectively make the slab a little thinner. During the installation of the floor, the fibers also offer much faster installation procedures on site because, well, we don't need to work around bar reinforcement, which is always a little bit of a logistical mission on site. But maybe let's also talk about briefly and importantly what they do not do. They do not prevent shrinkage cracking, and they cannot limit any crack width, and they also cannot prevent curling. So the only purpose of fibers, or the main purpose of fibers really, is in the strength design of the slab. So we talk about steel fiber reinforced jointless floors. So maybe let's have a look at the jointless aspect of it. Jointless floors aim mainly at what the word says, simply at the reduction of the high maintenance intensive joints in the floor. This has obviously many benefits: reducing the locations that require maintenance on the floor, improved driver comfort, and reduction of curled locations, and maintaining thus a better surface regularity. Jointless in this context means that we would cast the floor plates as large as we can during a day pour. This is usually limited by the building geometry, somehow puts sense to a grid, and by the concrete supply capacity, which is an important factor in the planning. These joints need armoring, as now all the joint openings are concentrated at much fewer locations, so these joints open very wide. And then the load transfer mechanisms are extremely important for the joint design and for the actual floor slab design. So yes, we will have joints. So jointless does not mean joint-free, but at a much larger spacing. So let's talk about joints. Since we have concentrated them now at much fewer locations, it doesn't mean that overall the whole floor slab has less maintenance. I like to rather say that the maintenance now is concentrated from being all over the floor to those joint locations every 30 or 40 meters. Those joints need prescriptive and targeted maintenance. If you ignore this, you will end up with very expensive and time-consuming repairs. And yes, maintaining armor joint is more expensive than socket joints, but it is happening at much fewer places. And the more scheduled preventative maintenance systems you actually apply into your operation, the better you can ensure that your joints deteriorate at a much slower rate and you save a lot of cost and money. So make sure you have a sound maintenance plan in place and it is followed by the operations managers. So there are a few very interesting industry developments that we experienced in the last couple of years. And a lot focus around the very issue that every floor is having to deal with, the joints. The most exciting ones are the emerging of the disruptive face joints. That basically means instead of a straight armored line, we have now all kinds of shapes of irregular surfaces, either a sinus line or a zigzag or a trapezoidal shape. And they all try to achieve the same good thing that we know since many decades. Every time we drive over a highway bridge, we see the finger expansion joints. And that enables expansion of the slab, opening of the joint, but at the same time, full contact of a wheel as it crosses this joint. There are several good usable products out there. We use most of them, and there are great improvement. I can really recommend that any traffic joint on a floor design should actually be such a joint. There are a few interesting ideas with post-pull and stored elastomeric joints out there. We use some of those in a repair effort for some joints that were badly deteriorated. While it is a very exciting concept, we found some durability issues at this particular case, but this was extremely high load and high frequency use. Nonetheless, a very interesting idea and worth considering for many applications. And lastly, mentionable is that we see upcoming shrinkage compensated or compensating concrete solutions, which are I call it the holy grail of concrete or holy grail of floors, getting rid of shrinkage altogether, getting rid of joint openings and curling. Technology is out there since the 60s. It's documented in various codes in the United States. But I must be careful. As I started in my presentation, we want to focus on risk mitigation. And the poor predictability and the missing integration into design codes of this technology needs to be considered if one wants to use that. I thought let's talk briefly about the history of jointless floors in South Africa that I experienced.
Sebastian, you've got about a minute to go. Is that okay?
That's good. Thank you, Gary. We got involved 2009 and issued a specification for tender for the new ShopRite Centurion, invited international and national contractors to join this tender. The contract was awarded to a UK company, and the jointless floors came widespread in South Africa quite quickly. And by now, local expertise in South Africa has beautifully picked up and have quite sound and wide tenders on this technology now. So you should consider this as a good tender for the next project. Maybe give me one more minute to show a few nice project pictures. Let's look at the floor picture of the ShopRite floors. This is some work that we did over the years with Gary on the ShopRite distribution centers. And in closing, I want to mention our Mercedes body shop project in East London, which was a very fascinating installation as a suspended floor slab, and the ground floor slab had 100 by 100 meter joint spacing with an educated client minding that there will be cracks. As long as you control them, they would be fine. And very interesting installation, lots of fun, and great end product. Thank you, everybody. And Gary, back to you.
Sebastian, thank you very much. If you can stop sharing your screen. Our next speaker is Daryl Eddy. It's appropriate to have Daryl after Sebastian. Daryl was part of the team that actually brought the first fiber reinforced floors into South Africa at that ShopRite facility that Sebastian mentioned. I've known Daryl for a number of years. In fact, my first project with Daryl was in Saudi Arabia when Daryl managed a flooring contractor. Daryl has since moved on and formed a company called Flat4 Consulting, and he acts as a professional advisor and gives guidance to clients. But more importantly, Daryl is also part of the team that was involved in developing or writing the 4th edition of the TR34. And hopefully Daryl will give us some of those insights today. Morning, Daryl. Sorry to get you up so early. I think it's about 6:30 in the morning in the UK, or on 7 o'clock. He's been up since about 6:15 with us. So welcome to 2021 and warm and sunny South Africa. Over to you, Daryl.
Thank you, Gary, and good morning, everyone. Not so hot and sunny over here. Storm warnings in the north of England, floods, gale force winds, on top of a lockdown number 3. Nice to be with you. Thank you for the invitation. Today we're going to talk about TR34 and particularly the changes over the previous editions. So our presentation today will focus on what TR34 is, the implication it has to all parties involved in floor slab design and construction. First question perhaps is to ask, what is TR34? TR34 is not a guide, it's not a code, it's not a standard, but it is described as a guide to design and construction of concrete industrial ground floors. And people say, well, if it's only a guide, is it really that important? Well, the truth is, if the specification says the floor slab will be designed in accordance with the recommendations of TR34, then it really doesn't matter. Contractually, it's in the documentation, and any future issues with that floor slab will be measured against its compliance with TR34. And certainly that could be the basis for non-payment or even worse, issues related later on if there's a problem on the job. So TR34 is a guidance document ideally aimed to provide all the information one needs to design and construct an industrial floor slab. Brief look at the history of TR34. The UK Concrete Society is an independent group, publishes information. It's the leading source of technical information in the UK. It produced its first guidance document on industrial floors back in 1988. So for those of us who were working in the industry back then, this was the beginning of changes to industrial flooring, from very old traditional checkerboard type installations to using American driven technology. The first edition was superseded in 1994. You'll notice it was only 3 years before the supplement to the second edition came out, primarily because FM2 TR34 second edition contained what many in the industry regarded as too onerous floor flatness requirements. And so the supplement in 1997 slackened those flatness and levelness conditions down a little bit. Although interestingly, by the way, the 4th edition goes back to the 2nd edition in terms of tolerances, because flooring contractors are so much more capable today than they generally were back then. 3rd edition, the brown one at the front, came out in 2003. But of course, technology moves on. So a 4th edition was needed for a number of reasons. The previous editions had only ever discussed slabs on grade, ground bearing floor slabs. Little hints in previous editions about slabs on pile, suspended ground floor slabs. but very brief commentary. So that needed to be included. Obviously, in the 10 years between edition 3 and edition 4, best practice changed. In addition, feedback from floor slabs design. The third edition really made slabs thinner. It worked on a number of issues that at the time were thought to be accurate, and with hindsight perhaps led to slabs that maybe hadn't performed as well as one might have expected them to. So that had to be reviewed. TR34 could now include more European standards and Euro codes, which over that preceding 10 years had changed too, as well as changes to the industry too. Another aim of the editing group for the fourth edition was to to avoid what had been done with the previous iterations of TR34, which was just to bolt on more information to each of the previous versions. So the final fourth edition draft was significantly reduced. Superfluous information was removed, it was condensed. We tried to shuffle the sections around to make sure designers or contractors had a bit of fluidity to the process. It was a bit easier to use. And as I said previously, the page count was much reduced. And so in 2013, TR34 fourth edition was issued and is now widely used, not just in the UK, but South Africa and further afield too. Changes over the previous versions? Well, significant changes. For those who have been regular users of TR34 over the years, some of the sections are similar, remain unchanged. Materials, concrete, joints, surface requirements. Some more subtle changes relate to the fact that there's much more emphasis on client education and client expectations and the advice, exactly as previously suggested by Sebastian, the need for regular inspection and the need for regular maintenance to make sure the slab's serviceability isn't compromised. The structural sections are now significantly different. Previous editions, there'd been some work examples in the appendices, things like that. Now we have entire chapters based on the structural design for a slab on piles or a slab on grade, much better direction regarding material properties, how to calculate them, how to measure them, how to analyze the loads imposed on the slab for pile supported slabs particularly. For example, the effective span between piles and in relation to the racking geometry, things like that. So much better and clearer guidance to the structural engineer. Material properties are perhaps the biggest change though. Back in the third edition, steel fibre slabs were designed using RE3 values. Well, that's changed. And now the concrete strength has to be designed in accordance with a Eurocode 2 equation, not RE3 values, using the notched beam test method based on BSEN 14651, which is the method specified, which makes a very level playing field. The TR34 also contains guidance to calculate the moment capacity of that slab, that composite material, whether it be fibres or rebar. A few other little tweaks to it. The editions 1 and 2 allowed some ground support when calculating punching shear. Edition 3 didn't. Edition 4 does now. Base plate sizes were limited to 100 mil by 100 mil. That's another change in the fourth edition. So interesting changes too to working practice. So for example, we've talked about fibres today. There are some interesting facts about steel fibre reinforced concrete. It is a fact, sadly, that the number of fibres you put in that concrete truck when tested often appears to be lower for all sorts of reasons. Clumping of fibres, fibre trucks not being suitable, not being new enough, mixed design having too much variability. So TR34 4th edition, section 6.2.2 suggests the use of a European standard to carry out fibre dosage checks on the wet concrete. And notice, interestingly, the specified minimum value of 85% of the design value as an average for a truck. So, you know, sort of accepting that there will always be a reduction in the number of fibers. So that's something the engineer has to consider. Does that mean we need to change our fiber dosage to be cognizant of the fact that we're only going to get all sorts of anomalies, but helpful ones too, and not too difficult to carry out fiber washout tests on site either. But it's not just fiber reinforcement that comes under scrutiny in TR34 4th edition. The use of welded wire mesh or fabric also requires some careful consideration and control on site. For example, this test report here referred to, project report number 2, produced by the Concrete Society back in the 1990s, actually considered some structural performance from very, very light mesh. And this is why the design in the 3rd edition reduced dramatically. But of course, anyone who's been on site to watch a slab reinforced with welded wire mesh with fabric will know how difficult it is for any contractor to get that mesh in exactly the right position, so that the design isn't compromised. So TR34 4th edition recommends that mesh has flying ends on one edge and one side, gives some direction about what type of spaces to use and minimum distances between spaces, so that the same degree of control is exercised over the floor slab as it is over the with mesh as it is with fibers. It also contains good guidance for slab on piles, how to make sure the pile cap construction is adequate, re-entrant corners around columns, and a number of other things. Flatness too has changed between editions. The 3rd edition in the appendices contains some suggestions about defined movement specifications to bring them in line with some European codes, which is exactly what you would expect, and that's now been brought into the main body in the 4th edition. Also, some other changes too to free movement tolerances. Property 4 is now property E, stands for elevation. That refers to the 3-meter grid of levels that a TR34 free movement survey would consider. Property 2 is now property F, flatness. This relates to shortwave bumpiness. And most interestingly now, there's no 100% limit in the free movement tolerances, but there is a requirement to calculate the 95th percentile of those property E's, which is the difference in elevation between adjacent points on that 3-meter grid. So this is how we control our overall levelness, one point to the next point, and also the overall control between the floor slab, finished floor level, and the target datum value.
Carol, you have a minute left.
Okay, good. So, in summary, what can we find in TR34? Well, Chapter 2 can help us educate our clients so that they actually expect what they should expect, not what somebody might have told them decades ago that patently is not true. Engineers have got comprehensive design guidance in Chapters 7 and 8, assistance in choosing the right materials and measuring our materials performance in Chapters 6, 9 and 10, good site practice for contractors, Chapters 11 and 12, an excellent Chapter 13 regarding maintenance of a floor slab and what we might expect from a floor slab when it's in use, and also for all parties involved in site control, some good advice regarding the elements we need to be checking and controlling during construction. So involve all parties, there's already been mentioned by Sebastian and Gary. Create a detailed design brief, also recommended in TR34. Get everyone around a table, virtually or physically, to make sure we build it as we'd like it built, and implement a robust quality control program using whoever, the site engineers, your team of engineers, Monofloor, anybody else who might be involved, and work together as a team. So my final slide, perhaps the best piece of advice in the new TR34 isn't new advice at all. This has been included in every iteration of TR34 to date. The best outcome for an industrial floor results from a well-integrated design and construction process. The biggest difference, though, is TR34 is now a document that allows you to do that. It contains all aspects involved and allows us to use it to make sure, hopefully, we deliver the best floor slab we can. Thank you, Gary.
Thank you, Daryl. you can stop sharing. Guys, just some administration. If you've got any questions and answers, just go to the question and answer area and enter the questions. We'll be addressing them in the question and answer at the end. Just something else, there will be, this is being recorded and this will be posted on the Relog website. There will be a link to it in our news and events page, as well as it will end up on our YouTube channel. So anyone that you want to share it with afterwards, you're welcome to do so. It's open, it's an open forum. Our next speaker is Dirk van Koeltren. He's the Chief Customer Officer and the Head of Technical Support at HCJ Joints in Belgium. So another overseas speaker, and I'm assuming they're a little bit earlier than we are. So welcome, Dirk. Thank you for getting up so early. Dirk's got a very interesting background and so on. I'm not going to take you through all of that. We can post that on the website and it was on the invitation. I think Dirk's going to talk a little bit about joints and joint design and the effect of load transfer and how HCJ has come up with their cosinus joint. Welcome, Dirk, and thank you. You have 12 minutes. We're not that strict.
Thank you, Gary. Good morning, everybody. Yeah, thank you, Gary, also for organizing this session here and bringing here some people from the industry together to talk about industrial floors. Just checking here to share my screen. Where is the button gone? Here we go. Share screen. So now you should hopefully be able to see what I see here on the screen as well. So yeah, thanks again for having me here this morning to talk a little bit more in detail about joints. Gary and also Sebastian already talked a little bit about it, and especially also about the importance of joints. And actually this first picture here is already telling quite a lot, where you see what joints actually have to do in industrial floor. And this is a little bit where I want to go more in detail through in this short presentation here this morning. Just to switch to the presentation, sorry. Okay, now it goes. So I think what is maybe necessary here to understand where we are today in the industry with joints for industrial floors is first of all to understand what is a joint actually supposed to do. So, and if we look at that from a general perspective, it has actually first of all to allow for horizontal movements. So why? And Sebastian already talked about that as well a little bit. Concrete tends to shrink. So yes, meanwhile there are some possibilities out there to limit that or to maybe even fully compensate that. But generally, if you take a cubic meter of concrete from the batching plant, you will realize it will shrink. So somehow we need to deal with that in whatever construction actually you build with concrete. And yeah, for flat floors on ground, yeah, somehow you need to compensate for that. So what you actually do with the joint is that you just tell the concrete where to move in order to prevent that it cracks somewhere where you don't want. So this is actually what it should do. Now, as we already talked about a little bit of efficiency of forklift trucks and things like that. So what you also want to do with the joint is actually to try to prevent that this joint moves vertically, because any vertical displacement you're going to get will lead to problems in later stage of the facility. Yeah, and in order to do that, you need to try to connect both sides best way possible. This is actually what you want to do as well with these kind of joints. Now, if we look a little bit more specifically into construction joints, which are used for jointless floors, as already also told a bit by Sebastian and Gary, these are floors where you just leave away all the saw cuts and you replace those by bigger floor panels with construction joints that you put yeah, every other 1,000 square meters more or less. Also, this is always depending certainly from the design that you choose for your floor. So what those have to do is that they actually have to allow for the horizontal movement, but the cumulated one. So if you skip the saw cut joints that you usually put every 4, 5, 6 meters, yeah, all this movement is actually accumulated in those construction joints. So they need to deal with this more movement. So when maybe a saw cut joint is moving a millimeter or two, such a construction joint can easily move 10, 15, 20 millimeters. So that's the construction joint has to deal with this. Yeah, again, preventing or minimizing vertical movements is again the same point as just before. Connecting both sides best way possible. Surely here even a bit more important, because if you accumulate horizontal movements, you will also accumulate more stress, which is then probably also leading easier to some curling. So this uplifting effect of the edges. And then what here comes on top, especially also, is to protect the edges and the way how this is done. Now, if we speak about this preventing vertical movements, make sure that you check what you actually get. So here that is just a little detail or a little example actually on when we talk about preventing or minimizing vertical movements and what we actually see sometimes in the industry. So that is the sleeve that goes over the plate. And here you see actually a relatively bad example of a sleeve that is also made of hard plastic. So there is no possibility of getting that compacted or in contact with the plate when concrete gets poured. So I think there are way better examples for this outside in the industry than the one that we got here just as an example. Now, if we speak about protecting edges, so then we are very much talking about a serviceability issue. So there we speak about a durability thing of the or the durability issue of the floor, and it's also affecting quite a lot of traffic. As already Gary said, pretty much everybody is now looking to get very good facilities that are very efficient. And so this is why here also that is extremely important when you look at the joints. So it is not only the flatness and the way the floor is built, but that is actually also a topic for the joint. So now the question is, what edge protection is actually needed to protect and create a durable solution when it comes to traffic? So we see out there quite a lot of different joints. Some have 3 millimeters, maybe edge protection, very thin ones. Then you see some with 5 millimeters. You see some with 10. But at the end, if we speak about traffic, all these millimeters are actually just a matter of time. So the only thing that you do with having there a thicker edge is that you buy just a little bit more time. Why? Because actually the effect is still the same. So if you have, it's like a car that drives over a bridge and you don't have the sinusoidal form. You always feel the bump when you drive over it. And this is actually nothing else than, I always like to compare it with a hammer that actually hits an edge. So you can take a big hammer or a small one. With the small one, yeah, maybe it just takes you longer. But at the end, if you have a nail, you want to hit that into a wall. With a small hammer, you also get it in. It's just take longer. So that means the effect of this bump, of this impact of this wheel on a straight edge is always there. And this is what is actually leading on long term to damages, not only to the floor, but also to the wheel. And that goes even further. So that is also then going into the machines, especially today, those equipments are very sensitive, quite lightweight themselves, so also quite sensitive to vibrations and shocks. All the electronic components are quite sensitive. So that you can imagine that this is quite a big issue. And yeah, this is also, as Gary and Sebastian already talked about, there were some changes in the industry, where we see now some sinus joints and other forms that are available in the market that is eliminating actually the cause of the problem. So, and those, yeah, when you have no wheel impact, you also have no damage that is related to that. So that means here you can really protect the edge, you can protect the wheel, you have less maintenance as well for the floor, as for the equipment that is driving. And yeah, you also have higher productivity, because usually what is happening if you have a straight joint or maybe even already a deteriorated joint, the driver will slow down automatically because he don't want to get the full bump when he's driving over the joint. So he will slow down in front of the joint, cross the joint, pass it, and then accelerate again. So if you imagine that this he's doing for 8 hours a day on all the joints that he's seriously often crossing, you will lose productivity. Which you have a good joint that is in good shape, it will not be the case. And meanwhile, that is quite well known and accepted in the market. So let's say that is a bit the effect on the serviceability. If we look more to the design aspect, so the calculation ultimate limit state, what you're actually looking for when we speak about connecting both sides best way possible is that if you imagine to have an action, a load on the floor that is 100%, this needs also to have 100% reaction. So I think that is physically quite easy to understand. And when you have an action, a load somewhere in the center of a slab, you have there a certain redistribution that is totally equal all around the load, as long as the subgrade is allowing for that. But this is something we assume in the design anyway. Now, if we have this at a joint, now the question is how there is the reaction, and that actually brings me into the second topic of that presentation of today, is the load transfer performance. So what is very clear, different materials have very different characteristics. It sounds obvious, but so far in the industry, quite a lot of people have just thought that if I use a construction joint, whatever it is, it will do the job. But actually, if you really look into the details of the design, you will realize that that's not necessarily the case. The performance of a joint is actually expressed or in load transfer, LT, so that's a kilonewton or kilonewton per meter, or maybe in a certain percentage. That depends a little bit on the way the design of the industrial floor is done. And then people are also partially speaking about load transfer efficiency, so what is called LTE. Again, in a percentage. So now what is that? It's quite easy. So if we have a joint that is 100% effective, or would be 100% effective, it would transfer 50% of the load. So now what does that mean? That means that you have an action, again, of 100%. It would equally redistribute the loads either side of the joint. But that is actually impossible, physically already impossible. I don't want to go into the details here. I think that would be way longer than the 12 minutes Gary gave me. But physically, that's impossible. Now, what is the reality? Now, this is just a very brief example on how materials can react. So you have here on the left side a joint that already failed at 45 kilonewton, and on the right side a joint that failed at 135 kilonewton. Now, it doesn't really matter in detail what it is and why it happened that way, but what is quite clear is that you look to different materials and they behave differently. So here you also see that you have here a certain loading, and that is the load deformation graph that came out of some testing. It's really just an example to demonstrate that yes, there are quite a lot of differences out there that will guide you to different results also in the design if you properly consider those. So, and that means in reality that you will face situations where you have maybe low performing joints or high performing joints that are able to redistribute in a certain way these percentages, because the 100% reaction is quite clear you need it to get everything equally, you know, so that is needed. So, but it's always a question on how good actually the joints are working. Now, so how does this influence actually the floor and its design? So first of all, you need to understand where is your floor. So you have a certain amount of static loads, of dynamic loads, and now there you need to choose and to make sure to understand where actually your floor is. Yeah, Gary, I see you appear. I saw your message. I know I have just 2 minutes left, so I will hurry up a little bit. So make sure you you properly assess where your floor is. What we see meanwhile, and I think my previous speakers already talked a bit about that, meanwhile we see quite high buildings with high static loads, high dynamic loads, so that quite often the demand of the floor is going quite far up, and that is leading to also quite high need on load transfer on the joint as well for dynamics as for static loads. So, and we are proposing this. There are other suppliers, other engineers out there that are actually providing this. Design checks for joints. Make sure you get those. Make sure that you get the right joint for your application. Because what you have to realize absolutely is that the joint is an influencing parameter of the floor design. It was underestimated quite a long time. I think meanwhile people are looking a bit more in detail to that, but it's anyway overlooked still today quite often. So make sure that there is the right appropriate choice of the joint. There are joints that are performing in different ways. If you, for example, 40% load transfer was for quite a long time and partially is still today an industry standard for the design assumption for load transfer. You have joints that are fitting into that and joints that are not. But the question is always, what is this 40%? Maybe the 40% of the applied load is a quite high figure, or maybe it's a lower figure where another joint fits into it. So make sure that you appropriately really look at that and that you have the right joint that fits to the design of the floor. So actually there are two ways to get those designs. First of all, you can get a designer who is including all the parameters into one design. This is out there. I have seen some of them that's available, that exists. And on the other side, that is also still available as it was in the past, that you have floor designs done by suppliers. But there you must make sure that they fit well together, so that if there is an assumption in the floor design made for the load transfer, that the joint is appropriate, the one that you choose. So that is what I want here to close with, is that which way ever you choose, make sure that the right properties are considered. Don't rely on assumptions. With this being said, I would like to thank you for your attention. Thank you, Gary, for having me here and to let me talk a little bit very briefly about the topic of load transfer. So I could talk for hours, but let's keep it short. And if there are any questions, they are always welcome also in the later stage. Thank you, Gary.
Thank you, Dirk. And thanks for, I see we're starting to get some questions. Our next speaker is Steve Sitaralis. Dirk, you can stop sharing. And Steve has quite an impressive CV. I'm not going to take you through all of that. But the important thing is I've worked with Steve before as well. And Steve is a consulting engineer similar to Sebastian. And Steve's going to take us through some of the interesting considerations that are happening today. And he's been working for the last 10 years with post-tension floor stabs in industrial facilities. That's also becoming quite a considerable option to fiber reinforced floors, and probably that we're going to end up with a hybrid of post-tension slabs that have fibers in them, which will have interesting joints. And I'm sure Steve's going to enlighten us on what's happening in this area of space. Steve, I don't see you coming up. Steve, good morning. Ah, there you are.
Morning, guys. Can you hear me?
Yeah, we can.
Can you see me?
We can see you.
I just want to start my screen sharing.
You'll have 12 minutes when you start.
Seem to have lost my file.
I think we have a copy of it. We could share it.
It doesn't seem to be coming up on my system yet. All right, if you could do it for me, Gary.
AB, can you just share Steve's presentation? We'll just run through it with him, and Steve, just tell us when to move slides.
Steve, unfortunately, you did not send me your presentation, so I don't have a copy of it.
It came through through a guy by the name of Kenneth. Let me just get my IT guy out here.
I'm wondering if we should move on to Peter Norton and then come back to Steve.
Yes, let's do that.
Okay, Peter, are you able to?
Sorry about this. I'll just see if I can.
Steve, we're going to move on to Peter Norton and come back to you.
Okay, thanks. I'll get.
Can everyone hear me?
Morning, Steve, Peter. So Peter has an even more impressive CV. But Peter is the managing director of Concrete Laser Flooring. I've known Peter for over 20 years probably, and Peter's been instrumental in putting together a lot of different floors, different floor repairs, different technologies, brought a lot into South Africa, and are one of the better flooring contractors that we deal with a lot of innovation. And I'm sure Peter's got an interesting story to tell us. Thanks, Peter.
Hey, good morning to everyone. And Gary, thanks once again for the invitation. It's a great initiative, and your comparing of events is a real skill, which is admirable. So thanks for inviting me on, and morning to everyone. We have been around for 23 years in South Africa doing floor construction and maintenance of industrial floors. We were the first company to introduce laser screeds into South Africa in 2006. And we were the first to introduce steel fiber reinforced jointless flooring in 2009 when we did the series distribution center. So it was just a year before Twintech came in and did the ShopRite Center, Gary. So I sort of put that out there. But we were very early adopters of steel fiber technology. We were also the first to introduce the plate dowel or the diamond dowel with armored joints into surface bed construction in South Africa, which revolutionized the load transfer away from the old keyway joint. We also introduced diamond polishing, which started in about 2003, and we've done some nice projects with that. We do a lot of grinding to surface beds for rehabilitation and attending to uneven levels and removing of coatings and adhesives. There's a picture of a polish which we did to a mezzanine, which just gives you a nice, dense, hard-wearing and dust-free surface. And then in around 2009, we were instrumental in developing our firms program in cooperation with Metzger Maguire from the USA, where we did the floor inspection, repair and maintenance services to our national clients to look after their floors. We've got some very innovative products to fix joints and damage in concrete floors. It takes about 10 minutes to set up, and can also work in freezers at up to minus 30 degrees. And we're a nationally approved coatings applicator for polyurethanes and epoxy coatings. So basically a lot that we can do with industrial floors, but I think we've touched on it through some of the previous speakers, is the function of a warehouse floor. And for us, it's really just to provide a durable wearing surface with as few joints as possible. And that's a high level look at it. But the demands on floors, as you pointed out, have increased over the years, and the floors haven't performed too well. Certainly the jointed floors haven't performed too well. And in Australia, the report or complaints about floor slabs is more than any other concrete. So they complain about floor slabs more than any other concrete. And it just seems that we would like to try and do the job a little better, which I think all the panelists involved in this morning is it's their jobs and their careers to try and do it a bit better. So the floor, as you said, is becoming increasingly important. We use higher racking with faster forklifts, and we want our floors to be flatter, last longer, but particularly to stay flatter for longer. And we just can't afford to have cracks and failed joints and potholes in the floor, as you say, that influences the whole supply chain aspect. So what's changed in the last 30 years is obviously fast-moving consumer goods. We've got much bigger warehouses. They're much higher. We've got much more efficient distribution with faster and better, more efficient equipment. The racking is certainly getting higher and higher. Forklifts are fast. In many instances, we have 24-hour operations on the floor, so the floors take a real hammering, and the wheels are harder. But basically, yes, we've got to get the good stuff out as fast as we can. And it starts me to say, what defines a good floor? And in our opinion, the optimum joint detailing is critical in floors. Whether you do a jointed floor or a fiber reinforced floor or a post-tension floor, where do you put the joints? And obviously you want to try and minimize the number of joints, whether they're armored joints or sawn contraction joints. We want to try and minimize them. The second aspect to a floor is it's got to be nice and flat. And whilst we put them down flat, it's very hard to keep them flat because they curl and they shrink and some settlement issues. So how do we keep them flat over a longer period of time? The third criteria is obviously we want a hard floor. It's got to be resistant to the abrasive operations. And also we don't want the floor to dust and go all over the packaging. And lastly, we obviously want a floor that has low maintenance, which will have lower life cycle costing, fewer repairs, which are quite disruptive to an operation. So in my experience in the last 23 years in South Africa, by far the most floors that we've put down are jointed and unreinforced. And an unreinforced jointed floor is essentially just a bunch of smaller floors joined together, which points to a lot of joints. Typically, you've got formed construction joints, which are nowadays mostly armored, but not all the time. And those joints are there when we determine how we're going to pour the floor. And then you've obviously got sawn contraction joints. The problem with joints, all joints, whether they're armored or sawn, is that they open up due to the drying shrinkage and the curling that manifests in concrete. Concrete is a material that shrinks. It starts with a lot of water, and the water's got to go somewhere, and some of the water is absorbed by the cement, but a lot of it evaporates and moves out of the concrete, and that is drying shrinkage. And that creates an impact point. So curling happens in a floor because you've got moisture in the floor. It has to move out, and you start getting warping of the concrete panels. And this happens to small jointed floors. It also happens to 30 by 30 meter steel fiber reinforced panels. They also curl. And that curl creates voids underneath the slab, and you start to have movement of the slab under load. That's just a picture of what curling starts to look like on a floor. And you create these impact points, which then get hammered by the hard wheels of the polyurethane reach trucks, and even the little pallet jacks are surprisingly fierce on joints. And this starts to happen where you get damage to the concrete. And it can lead to sort of rocking of your panels, which again is not what you want for your operations and your forklifts, operator fatigue and danger and so forth. Curling can be remedied with injection grouting, but that becomes quite a process, and it disrupts the operations. So over 200 USA distribution facilities were surveyed, and by far the problem was joints on their floors. So again, modern floors need to eliminate the joints simply because loads have increased and wheels have got harder and smaller, and I think we're all aware of what we're talking about here. And facility managers just cannot deal with these joints because once they start to deteriorate, they have to be fixed to look after the forklifts. And that's one of the main reasons why we need to eliminate these joints. They cause damage to the wheels. They cause significant load tippage. If you can believe this was a floor that was actually functioning, where the joints got to such a degree of deterioration that load tippage was a common day occurrence. Obviously, your forklift maintenance costs go through the roof. And joint repairs are expensive. We've built a business around fixing floors, and we can fix them. We fix them very well, but it's expensive and it's disruptive to clients. And when you fail to maintain your equipment properly, you get malfunction and maybe even a catastrophic failure. So it's something we want to steer away from. We want to have safe operators in these facilities, and we want the forklifts to be able to operate quickly and smoothly. We do a lot of work on aisle renovation, aisle repair, which have suffered joint damage and curling along the joints. So that's becoming quite prolific. This is a typical example of how we'd go about doing a joint repair, isolate the joint and get on with it. But obviously it disrupts how people operate their warehouses. So they're reluctant to do it, but they have to do it. So this all leads to tenant frustration and owner frustration, which is understandable. So the hidden costs are well documented, but there's just a summary of them, and particularly your reduced building value over time. And then obviously your operator fatigue and just general staff morale. So if you look at a traditional floor of say 3,000 square meters, you're going to run about 1,200 meters of joints or cross so many joints in a passage of traffic. We prefer to look at things like steel fiber reinforced floors or shrinkage compensating floors or even post-tension floors. Post-tension floor is a very good floor. For us, it's just a constructability issue. It's quite a tricky thing to construct, and it takes some time, but it's an excellent floor. We've thrown our hat into pursuing fiber reinforced and looking at shrinkage compensating, where we can eliminate shrinkage and create sort of 3,000 square meter panels with no saw and joints, and then apply some decent armoring to the joints with the disruptive face jointing type of application, and these cosinus and wavy joints that we think are the way forward. But any way we can do to eliminate joints. So our shrinkage system, it really brings in the products with the equipment, but also with the artisans. We're in the bottom end of Africa, and we've got artisans that have to do the work. So we need to work very closely with that. So we want to place about 3,000 square meters a day, and we want to have high flatness. And it starts with basically high quality concrete with fiber reinforcement, and then with a type K shrinkage compensating cement from CTS in America, good armored joints, laser screeds to place to high flatness, and then to warranty and a maintenance offering. So key properties is eliminate joints, reduce abrasion, increase placement sizes, and minimize long-term stress loss and creep. So the testing is in accordance with ASTM, and we look for an expansion of about 0.045% at 7 days. We target about a 50 MPa compressive strength. Just some detailing is very important around your joints. We still adopt proper detailing to columns and the like.
About a minute left.
Okay, I've got 1 or 2 more slides. There you can see armoring. Where do we put the armored joints? We need armored joints, but let's have a discussion about where we put them, and then placing and finishing. We place with laser screeds. We finish with ride-on power floats. We do it in a closed building. That's also very important. We need to get it in quite quickly because programs are under serious pressure these days. And curing, it's the last thing that's done on a floor, but for us, it's the most important thing to do. So, yeah, I think jointed flooring is okay if you want to do it. It's obviously your cheapest, but it has to be maintained, which is very disruptive. So we are big proponents of going jointless in the various forms. Yeah, that's all I've had to say. Thank you very much.
Peter, thank you. That was a great presentation. I'm hoping I see we're getting lots of questions. We'll come back. Some are being answered, but we'll go through them in the panel discussion. Steve, are you okay, or should we?
Yeah, I'm good. Thanks. I'm good. I've got right.
Okay, great. Well, welcome back, Steve, and let's share your screen.
Okay, you stopped my video. I'll share my screen.
On your video, allow you to start video. There we go.
Can you see something?
We're seeing you.
There's a breakfast with Relog, industrial floors and warehousing and distribution centers.
No, it's not shared.
Not shared. That's crazy.
When it says share screen, just click on that actual document when you click on the share screen. There we go. Something starting. Well done.
Because you cannot start your video because your host has stopped it. I'm not too sure if that's...
No, you're on video. That's fine. We can see you, and we can share your screen. We can see.
Okay.
Then just click on slide 1 and then put it into presentation mode.
Where would that be?
Just click on the first slide at top left of your presentation.
There's something in the way there.
Or just use the projector at the bottom and just go up and down with the slides until you get to the slide you want. There's a little picture of a screen. There we go. Going up one, go up another one. Down.
Can you see that?
Yeah, no, we can see it. Just keep going up. You're on slide 5 at the moment. There we go. 3. There we go.
Okay.
Okay.
Oops, sorry about that, guys. It's the first time I'm doing a webinar. It's been a little bit of a teething problem there. I want to discuss the post-tension slabs on the 4 headings, basically background and reasons for PT, and then criteria used, and the design philosophy we normally use, and then the current performance and designs we've actually carried out in the market, and then basically our future designs.
If you can try
Starting
with
with the...
minutes, Steve.
Again?
Try keep to the 12 minutes.
Yeah. Starting with the background, let's start with some history on post-tensioning. Post-tensioning ground floor slabs have been around since the early 1960s. Are you still seeing my... Is it still working correctly? Okay, the post-tensioning has been around since the 60s, and since then, millions of square meters of ground-supported slabs for residential, commercial, and industrial applications have been constructed. The applications have been particularly effective in dealing with problematic soil conditions, such as heaving clays, collapsing sands, and areas where potential sinkhole or subsidence occurs, and it's especially effective when you use it with a piled solution where you have a piled slab on the piled scenario. Looking at the primary advantages, the first big advantage is that it's really truly a jointless construction. I know we've discussed jointless as being 30 by 30 meter slabs or 20 by 20 meter slabs, but in the case of the PT, we normally get away with slabs up to 200 meters long without any joints. And that proves very, very effective. Another advantage is the elimination of shrinkage and the flexural cracks throughout the lifespan. Obviously, lower life cycle costs without the joints. We have enhanced serviceability because of minimal maintenance and facility downtime. We have better preservation of floor flatness and levelness because you don't have any joints. You have a decreased slab thickness. You have an increased load strength. You have an interesting characteristic where you have a resilience to recovery. So in other words, if you can overload a slab, by taking away the load, it recovers quite easily because your ultimate tensile stress of your cables are never really exceeded. So you actually recovers to its original state quite readily. And then you have the advantage of having unlimited panel pore sizes, which obviously assists in you can go to a 50-50 panel or a 60 by 60 panel. You're not restricted by the shrinkage and the shrinkage requirement, the shrinkage restrictions and the curling restrictions. Disadvantages, obviously we've mentioned the costs. Gary, I think you mentioned those quite extensively, but I think if you value the costs or you measure the costs against the total cost of the project, you find these costs are totally mitigated by the low maintenance requirements and your effective usage of your slabs without having the maintenance type of problems that you normally have. The other problem is the danger of damage to cables. There's obviously the danger of people drilling through the slab and hitting the cables, or coring through the slab, or cutting out having large cutouts on the slab. But essentially, we haven't had a problem with any of our slabs in that regard. And where we have racks installed, obviously we limit the drilling to about 65 or 70 mils, and that the contractors or the suppliers of the racking are happy to do that. Coring, it's very easy to scan the floor and check where the cables are, and then core when you need to. And large cutouts are also possible. They are a little bit more expensive, but it is a solution that you can actually, there are solutions where you can actually open up the floor, expose the cables, anchor them, and then basically cut them and then re-anchor them. So those are basically the disadvantages. Looking at the design criteria, we firstly, obviously, the designs are normally dictated by the high rack loads or concentrate loadings from the high rack loads. We start off by making an estimate of the slab thicknesses, which is based on the geometry and the pore sizes and the loadings. We estimate the subgrade or subbase drag, and we calculate the friction losses that we expect in the cables for the specific geometry we've utilized. We then calculate long-term losses, calculate the creep, shrinkage, PT relaxation, and take that all into account so that we've got an effective pre-stress at the end of the day that we work with. Then basically we analyze the loading effects using the Westergaard equations or finite element on the elastic foundation scenario. And then obviously we verify that the total superimposed stresses and deflections don't exceed the allowables. I've provided a little simplified 2D animation here, which just shows you what the effect would be on the animation's not working. When you have a compression and a tension scenario, when you have a straightforward loading condition where you have the compression and tension being equal, your stresses are your strength of your slab is dictated by your tension in your concrete. Now, essentially, that's generally about 1/10 of the compression stress of your concrete. So if you've got a 30 MPa concrete, your total strength of slab is determined by your tension, by 3 MPa of tension. If you put in a cable and you compress it, you can reduce that tension that I showed you as tension down to 0, and then you've got suddenly an effective strengthening of the slab, a remarkable strengthening of your slab just by doing that. Our next item that I want to discuss is quickly give you an overview of current applications and current usage of the slabs. For conventional applications, which we mean by warehousing in industrial, to date we've successfully completed more than about 600,000 square meters of PT slabs. The slabs have been monitored over their lifespan. The oldest one's about 9 or 10 years old, and without exception, all have been virtually maintenance-free. The only areas where we've had some sort of maintenance has been where we've interfaced with, let's say, an existing slab or a existing hard stand or the loading dock or an office block floor. Because there's such a minimum amount of joints, the costs are obviously minimal. You just have to fix up for a 25,000 square meter warehouse, for example, you have to fix up one joint type of thing. So it's very cost effective. We normally have slabs, so we've been working with slab sizes that have varied in continuous lengths from about 50 meters to about 250 meters. Slab sizes, slab thicknesses vary from about 140 mils to 200 mils. Concrete strength from about 30 to 40 MPa. Post loads from about 30 kilonewtons to 180 kilonewtons. We normally cast the slabs on a slip sheet and 20 mils river sand, obviously to minimize the frictional sub-ash drag. So those are essentially a little brief picture of what you can get. Looking at the constructability of it, it is a little bit more difficult to do, as Peter Norton mentioned. It does take a little bit more time, but my argument is that if you spend a little more time, a couple more weeks, maybe a week or two extra on doing it properly, you end up with a floor that is remarkably maintenance free, and although slightly costly, the costs are quickly mitigated through no maintenance issues. This is a warehouse we did for, we're doing for Toyota. It's developed by Investec, and it's almost 200 meters long in one direction and 150 meters long in the other direction, and essentially it's joint free. This is the same warehouse. Just shows you the principles of how the cables are placed in the middle of the slab. Generally, they are actually spanned from one end of the building to the next end of the building, so you've got a full continuous cable that has no joints, that has no breakages in it. Like I said, it is a little bit more of a hassle, but at the end of the day, your product it's worth it for the product you get. There's another picture of it. We also utilize it in dolomite applications very successfully. Approximately half of the 600,000 square meters of slab to date were designed to accommodate dolomite sinkhole conditions. We had sinkhole sizes varying from 5 meters to 10 meters diameter that we had to accommodate. Now, the PT solution lends itself ideally for such an application, as the cables provide continuity of integrity. You've got longitudinally and transversely, you've got cables in the sort of almost like a net effect. And as such, you get a pretty robust and resilient solution. It actually can, because can form a continuity effect, you can actually span sinkholes in excess of general design requirements. We've had a situation where we've had a sinkhole occur and we didn't even know it occurred. Luckily, it was the edge of the slab so that we could notice it, but at the end of the day, the cables were very effective in mitigating that sort of scenario. Moving on to special applications, in addition to the PT solution, in addition to what we've done before on these things, we used it in specialized situations to provide basically unique solutions. For example, we use it as an alternative for the slab for South African breweries, which was required to carry a number of heavy silos. The design called for a 1 meter deep conventional reinforced slab with Y25s at 200 in both directions, top and bottom. We managed to redesign it and get away with a 500 deep PT slab, which resulted in the resolution of a number of logistical and practical problems. I mean, casting a 1 meter deep slab with Y25 top and bottom, you can imagine the nightmare involved in that. And there was approximately a 40% cost saving. Another truly unique solution has been the use of a hybrid solution where we used PT and steel fibers for the internal and external hard stands for a workshop for Komatsu, which was developed by Investec. The loading from the proposed machinery and equipment on the hard stands reached up to about 150 tons. The slab was designed accordingly, and we managed to get away with a 200 millimeter thick 40 MPa slab with only about 35 kilograms of fiber. A couple of photos of that you can see.
Steve, you
yeah, I'll finish off now.
Thanks.
and you got tech equipment driving on the machine. We really haven't had any problems with that other than at the joints and when the guys do donuts on the surface with the machines. But otherwise, it's performed remarkably well. For future designs, we're looking at going for the hybrid solution that we worked at. Komatsu worked out very successfully. So we're looking at in the future of doing a hybrid solution with post-tensioning and fiber, and in addition to that, possibly using some shrinkage compensating additives. That way, I believe we'll probably get very effective and very cost-effective and almost a Rolls-Royce solution for floors. Thanks. Sorry about the delays, guys.
Thank you, Steve. So at least we got to see all about post-tension slabs. I can tell you that my first post-tension slab was in Australia when we did a job for Priceline. It worked out quite successfully. There are some challenges there, and we'll discuss them in the panel discussion. Yeah. The last speaker is the Technical Director of Monofloor Technologies. Henry, morning. We've got you up on the screen. And so Henry's going to close off and give us some further insights into floor construction, floor design, and applications. Thank you, Henry, for coming on the call. 12 minutes.
Thanks, guys. Are we on?
Yeah.
All right. Thanks for the time, Gary. Thanks
Henry,
for
Henry,
yeah.
You are sharing your presentation mode side. So we're seeing.
Oh, sorry.
Yeah,
wrong way around. Just hold on
around.
a second.
Yeah.
Seeing the same again.
No, that looks like it's better. That's perfect.
Okay,
Great.
Perfect. There we go.
Good.
Sorry, just wrong way around. Hi, guys. Thanks for the time. I'm not going to go into much detail or specific details. I'm more going to focus on the story that I would like to get across. That's well in line with what all of the panelists have spoken about today. So it's about creating an industrial floor, but from a different perspective. I want to run through an introduction just to show you what I'm about and what I'm going to talk about. I want to talk about design, works execution, and then conclude on everything after that. But based on the perception that I mentioned. Okay, so to kick off, what is a floor? The floor is arguably the most valuable asset of an industrial facility. So it's not only a part of a structure, it's also an integrated part of the materials handling system. So you see, it's not a contributor, it's the platform for all operations. In other words, it's not a slice of the operations cake, it's a plate on which the cake is served. So the life cycle of a facility's operational performance is directly related to the floor's system's durability. It's about the durability focus, not a structural integrity focus. As durability decreases, more defects will start to manifest, which means more maintenance to the floor and the materials handling equipment, like Gary mentioned, which is a costly exercise. And as a result, you'll have a reduction in productivity, which is most expensive of all. And then the cycle just repeats itself at an exponential pace because more weak spots in the floor shows more deterioration or re-deterioration, more maintenance, working again and again, decreasing the productivity of the facility more and more and more. The moral of the story is that we need to create a floor system where durability is a primary target, where the design and construction is based on operations in the short and longer term, rather than just focusing on structural soundness. So, do we create a durable floor solution? How do we create it? I missed a slide. Sorry, guys. There we go. That's the slide I want to be at. How do we create this durable solution? We choose this system strategically. In other words, what system will give flexibility in the longer term? And if you don't need the flexibility in the longer term, how can you create a system that's unique to its application or that you want to achieve or work with? To budget the process wisely, money is always a big topic or a frowned upon topic when it comes to creating a floor. But where do we allocate the funds? Do we spend more on products, less on the operations? Do we appoint an engineer, consultant, flooring consultant, and a logistics consultant, or just a contractor? It's very important how you budget where you're going to spend the money, looking at the longer term. We need to plan all the stages thoroughly. Planning. Most errors come from negligence to detail, and not the big ones, the smaller, less important details. And that's normally where the errors creep in after the floor's being handed over. The reason why I put in point number 4 is when it comes to products, there should be no exceptions for quality of any sort, or even to save time during construction. If to save a week in construction time because you're using a quicker to install joint, or like Steve said, post tension takes a longer time, but the time you save now is a lot of time you'll lose going forward in the operations of the facility. And then we need to execute consistently. Consistent execution that is average is much more beneficial or good than award-winning pause that cannot be done repeatedly. So the secret is to find the best formula, taking project-specific challenges into account, because the floor has never been done exactly as per the drawings and specifications. It's about a real-time influence. Okay. So, 1 second. The previous speakers went into specific details on all items related to floors. Thanks for that. Learned a lot. But I will not be going into depth as it's been addressed, all of it already. I'm just going to share with you headlines just to maybe refresh your thinking. When we're considering a design based on durability, joint layout is very important. We need to focus on panel sizes. What's the panel sizes we require? Not necessarily the biggest panel sizes. Of course, the bigger the panel sizes, the less the joints, which is a big win in some cases, but it's not always about that. It's about what suits the operations that's going to go on the floor. If you've got rubber tires, for instance, external hard stand facility, a container laydown area, you don't need to worry about arrest protection. When you work with packing or stacking of items or products directly on the floor, you're focusing on a distributed load rather than point loads or distance from joint edges or load transfer on joints. So all that I actually want to get across is it's about focusing what's needed for the specific use and not a copy and paste design like we've known for years until floors have come to the point where it's now, like Gary explained in the beginning. Armor joint, unarmor joint, there's disruptive face joints. There's a few on the market. Our Engelhof client they've got a very impressive joint that they use. There's some from Permaban. There's a few in the market. It's just about, again, selecting the right joint for the right job. Abrasion resistance, very important, and then surface regularity. which is a very hot topic. When it comes to industrial floor, we talk about surface regularity. To me personally, it's not about what the standard says it should be. It's about what the material handling equipment needs. So do we have a floor that's flat enough for the equipment to, or flat and level enough for the equipment to work on it? And the important thing is not only the day when we hand over, floors change. Now, floors settle, curling appears, happens over a period of time. Floors change. So are we geared already for the 5 or 10 year plan, or are we just handing over the shiny floor? Okay. Planning, understanding, and confidence when we get to the execution of a floor. Prep works, detailing, and methodologies need to be understood by the contractor and also by the design team or logistics consultant or whoever is involved to make sure that there's that everybody, the expectations are met or are going to be met. And also, if the flooring contractor is understanding what is required from him, if that's clear, that all needs to be sorted out before project starts. It's very important. The mix design needs to be handled before you start and improved during works. Concrete delivery is major when it comes to the installation of an industrial floor. So you need to have the planning ready before project starts, because again, constant average supply tops any award-winning concrete that can't be supplied consistently. Doesn't matter if it shrinks zero. If you can't supply it consistently, you're not going to have a successful end result. Pour sequencing. Are we planning our pours correctly? Execution methodology. Does the contractors, again, understand what needs to be done? And do the design team or the client team agree with and understand how the contractor wants to do it? A lot of the times it's got the same destination, just different ways of getting there. But it's important that everybody understands. And then housekeeping and protection, making sure protected against environment. Are we working clean? Are we stacking our joints correctly? The la-di-da nitty-gritty stuff, but that's really important because it can have a major impact after the floor's done. So what we do at Monofloor and what we can recommend is always to set up a quality plan. I have a quality plan ready before the floor starts. Make sure that from the client that came up with a concept or what he wants to the guy that's executing the floor is in agreement with what they are planning to do. If there's issues with any of the specifications or a pragmatic problem that can't be solved, it needs to be sorted out before the floor starts, not during the floor. All right, thanks, Gary. I see your message. I'm wrapping up.
Thank you.
Quality plan is key. So how do we execute with the durability mindset? We've got our planning in place. We've got a quality plan that we want to follow. We execute process-based and not product-based. Are we focusing on having a system or handing over a system over a period of time, or are we handing over the shiny floor, handing over the product? Quality management and not quality control. We want to have an influence while it's being done and not after it's already completed, to have a real-time impact and not just a data file afterwards. So if we can improve the project as it's being executed, you're looking at the best end result. System responsibility, not system selling. Have the contractor or the team involved for a longer period so that they buy into the system and not just handing over. Attract the user. Guys, we always forget about the guys who's going to use the floor. The guy who needs to clean the floor, who needs to wash or keep the joints clean, giving him a floor guide and involving him in the decisions being made already gives years on your floor. So what I want to get to is we need to build and foster pride in the operational contribution of the floor and not the shiny product that we want to hand over. So to finish off on my last slide, I want to leave you with this. Should the cost of creating a floor determine its value? Or should the value of the operational platform over a period of time determine the cost? I thank you guys. Thank you, Gary. Thanks everyone for having me, for giving me the opportunity to teach, and more importantly, to learn. I hope that somebody could take something from this, even if it was just a thought. Back over to you, Gary.
Okay, guys, morning everyone, and morning to all the panelists again, and morning to the audience. Okay, so we have run a little bit over time. We have about 10 minutes left for questions and answers, or a bit of a panel discussion. What I have learned from this is the most important side of it is planning, design, and then the execution. And in the execution comes to your selection of your concrete, your joints, your technology, whether it's post-tension, non-shrink, methodology, and then there's challenges that you're going to get. Do you have the time to put the right floor in? One of the things that we haven't touched on is the time for the floor to cure before we use it, and what happens when we load the floor, which restricts shrinkage and contraction, etc. Do we have the costs measured, and so on? So we know that a post-tension floor takes longer. Do we have that time in the project, and how can we manage that? When we think about the environment we work in South Africa, the consistency of our concrete batching plants, the time to deliver to site, that you can actually get enough trucks to site within a guaranteed period, so that you can maintain that your concrete flow is arriving at site as you're working it. Because if you can't reach that concrete demand, you can't actually construct that floor. A lot of it, what you see today, is more experience than science. It's a bit of a black art, putting floors in. And it's going to come down to the costs at the end of the day. And as I say, I think one should, our hardest job is to get customers to understand that the cost on the floors is not the key thing to be driving, it's the design. There were some good questions. We're going to be answering them in writing and putting them up. Is there anything the panelists would like to discuss? One of the things that I would like to ask Steve, and maybe it can be addressed in a bit of a panel discussion, is obviously with a bigger panel, you still have a big joint for the construction joint at the point where you have to tighten and tension the floor. How does that joint get designed and managed in such a way that it doesn't influence the operation, that you can travel seamlessly across that? And that's been one of the biggest challenges with joint design and construction joints, and and eventually this has come up with the new permaban and the cosinus joints, which have the different shapes which allow for a much smoother flow. Steve, is there any feedback on that? I know that was one of the problems we had in Australia with their floor joint. Even though the panel, there was less joints, when we traveled over the joint, it was a problem.
Gary, essentially, we haven't needed to address that issue for any of the projects we've done. So we've never been more than about 250 meters in length, and we've managed to get to 250 meters without a joint at all. So in other words, you don't have any joint. You only have it at the edges where you have a, let's say, for example, you have a brickwork wall or something like that, or you have a loading dock. And normally your loading dock is provided with a little sliding plate that slides over the slab, so you don't have an issue with the loading docks per se. So essentially, if you're going to go for more than 250 meters, which is what we're looking at in the project that's coming up, we're going to have to address that issue, and we've had a few thoughts on that. And the one important thing is that we may have to put in a temporary joint. Because remember, it's only one joint in a length of 250 meters, or let's say you're going to go to 300 meters or 350 meters. You put a joint in the middle there, you'll have one joint that you'll have to deal with, and you can come in after it's shrunk, after about a 6-month period, you can come and fix that joint up and repair it and do something to it. That's what we're looking at the moment. Alternatively, if we're looking at some sort of additive to reduce shrinkage, that joint can be typical cosinus top joint.
Anyone else have any experience? Daryl, have you had any experience with large panels and post-tension?
Yes, yeah, I think the post-tension system is an excellent system, but that tensioning strip is an exceptional problem always. You've got to find somewhere in the floor slab to have a pair of joints close together that are particularly poor in terms of usability, and you've got to find somewhere to hide them where they're not likely to get very much traffic. And I'm not sure putting them at a dock strip is a good idea where those little trucks will access them all day. You've just got to be smart about your positioning. It might well be you need to be less ambitious, so you can position that tensioning strip somewhere where it's less likely to become a problem. Or, as you mentioned earlier, maybe a combination of something like the RCR signature strip might protect that, both of those edges of that tensioning strip if it's between two panels. In Australia, sometimes they put them on the outside of the building, which helps. So I think it's definitely something building specific, but it is the biggest challenge of PT slabs, second perhaps to the contractor's challenge of trying to produce flat slabs with tendons everywhere. Sometimes they use bridges to use laser screeds. Some contractors do it flood pour and then rectify the surface. So a great system, two big challenges.
Guys, any other issues you'd like to bring up? Not necessarily on post-tension floors, on pitfalls and things to watch out for in conventional floors, fiber reinforced or joint application, joint installation. One thing that I've seen is that you actually install the joint skew, it changes the properties. So I think that's obvious is your attention to detail. Sebastian? Peter?
I had a very good question in the in writing, and I thought this is a worthwhile question to raise here, which is about if you look at the system, overall performance of the system, we mustn't forget about the platform. So the design of the building platform, the testing of the natural ground of the subgrades and the design of the platform to suit the demands of the floor is actually 50% of the deal. So platform design and floor design should be very closely tied. If you have the opportunity, have them done by the same person, or at least make sure that there is very active collaboration between these two designers. If the platform fails, the settlement or similar effect, that will immediately translate through into the floor and will have effects on these floor surface regularity immediately and kind of cracking and all other things, and it is next to impossible to repair.
It's a very good point, Sebastian. Thank you.
So if I may add, Gary, just quickly, I think floors are, I think it's the hottest topic today. In anything in concrete, you know, if you want to go to an event or a seminar or something about concrete, industrial floors will always be mentioned. I think it's a code that hasn't been cracked yet. But what we are doing is we are trying to manipulate or trying to get the closest average or finest line between what is needed and what can be provided, especially when it comes to joints. Yes, the bigger we go with panels, the less joints we've got, so the less maintenance on isolated joints, but we've got bigger joint openings. So now we are trying to introduce shrinkage reducing additives or volumetric control additives to improve the shrinkage, but it's still not something that has been a proven contributor or end result. So what are we using the facility for? Just to get back to what are we using the facility for? And if we have extra joints, as long as they are placed strategically, like Daryl said, it's all about planning and making sure we understand what are we going to get out of the facility. And that's the crux of the case.
Thank you. I think one of the things that I don't want to take too much longer. We're running over time, and I have another meeting to go to myself. We almost need to set up another breakfast with Relog webinar where we actually don't have presentations. We actually have the same panel just in a discussion mode for half an hour, 1 hour. I'm not sure if the audience would like that, and people can send us notes on our Facebook or on Instagram or whatever, LinkedIn and so on, and let us know, or send us an email to say that that would be something interesting, doing our breakfast with Relog differently and just have a straight panel discussion. I think that's a very hot topic. And just to close off, one of the comments I would like to give is I met with, in Saudi Arabia, we're doing a floor for a grocery retailer, Panda, and I met with a floor additive supplier who supplied fibers and all different things. I think the company was a Belgian company, De Gussa. And the guy said to me, what would you like as an ideal floor? And I said, ideally, I would like a piece of concrete that runs from one wall to the other wall of the warehouse without any joints, that's perfectly flat and has no shrinkage, no contraction. And that, to me, as the guy operating the warehouse or designing the materials handling on top, I would like total flexibility to drill holes into it, to put racking on it, to put the loads on it, have no joints, no variation in level, and that would be the perfect floor. So up to you guys to actually come up with thinking about that and designing that technology and developing that. And eventually we at Relog will be happy, and our customers. But thank you everyone for making the time. Thank you for the audience. And our next breakfast with Relog session is planned for late in February or early March, I'm not sure. And we will let you know. We'll give you input on that. Thank you very much.
Thanks, Gary.
Thanks, Gary.
Thanks, guys. Thanks, everyone.
Thank you, everyone.
Thanks, guys.